And so what do you want to do? You want to look at F inverse of epsilon. So F inverse of epsilon will look like this. And yeah, so you can sort of show that since this is the global minimum, this will have index 0. So this will literally be your attaching a 0 cell, which you thicken is just going to be an n base. We saw in the case of this. This is an n base, but given this is an n base. This is, let's say, so even this, everything up to here, even this is an n base because of this theorem. Because I'm not passing through any critical. So I can go all the way up to this point. All the way up to here. This is my start. And on the other hand, you could show that if I just look at this part, this is also going to be an n base because this has index n. So if I use the coordinate system here, if I look at F inverse of 1 minus epsilon going to this will come out to be an n base because of the index n. So topologically I have this to be an n base and I have this other thing to be an n base. Right? But they are identified with two standard n base using some homomorphism. So when I do this with this, I know what to do here. When I'm doing the corresponding dn copies, I have to use the homomorphism to do this. So I map this to dn because my coordinate system allows me identify this with an n base. I can identify all of this with this smaller thing, another theorem. This is identifiable with a dn, that's the lower hemisphere. And now I glue them here, I identify the two hemispheres there by the identification that's happening. So the proof is literally that. You cannot literally identify the two dn's as this because the boundary of the dn's are standard, but these are not dn as presented. Choose this identification with this text. But the proof is literally that this is a copy of the disk, this is a copy of the disk, we're doing two copies of this along their boundary by some boundary. That's okay. So yeah, in terms of that, you can drop this condition. I think Miller later on wrote a small article where if you do a bit of work, you can drop this condition of non-degenerate. So even if you have two degenerate critical points, it still comes out that it's a sphere. So it's a nice technique. So now the point is, okay, what can you do with this? Well, if you are someone like Miller, you can do a lot. So I'll simply mention because I don't want to go into the whole construction of exotic spheres because there are other things that I want to talk about. But what he did was, he was trying to study S3 bundles over S4. So S3 is the 3 sphere, S4 is the 4 sphere. So for those of you who know bundles, fine. If you don't, then you say that a space is a bundle over B with fiber F. Simply means that the space locally looks like B cross F. So if you have seen tangent bundles, the tangent bundle is an example of a bundle because the base is the manifold F and the fibers are the tangent spaces TTF or R. Right? And so similarly, you can have lots of other examples. Standard torus is a fiber bundle because it's S1 cross S1. So it's kind of trivially fiber over one circle with the fiber being the one. You have seen the Mobius strip. That's a fiber bundle. The core being the circle and the lines which get twisted as you move around, those are the fibers. Right? They're just the lines. So yeah, so we have many examples. So the point is he was looking at S3 bundles over the 4 sphere, which came from vector bundles of N4. So we look at an R4 bundle over S4 and then look at the unit sphere in each copy of R4, which is an S3. But unit sphere in R4 is S3. So he was studying such 7 manifolds. It turns out there's a lot of them. In fact, there's Z cross Z, many of them. You put orientation. And among them, you could identify a class of them as being homeomorphic to S7. And how did you do that? So you have all these S3 bundles over S4. So you choose specific ones according to the construction. and then you claim that that total space, which is a 7-dimensional manifold, because the base is 4-dimensional, the fiber is 3-dimensional. That 7-dimensional manifold is topologically the standard round. To prove that, we construct a Morse function on that 7 manifold, and then he shows that it has 2 fields. Then Reed's theorem tells you that 7 manifold is only one. That's the, I mean, it still requires a lot of insight to get such an example. That's the easier part of the paper. The harder part of the paper is to now show that these S7s that you have constructed, apart from the obvious one, is not diffeomorphic to the standard ground sphere. That requires a bit more work. That started off a whole bunch of things, looking at non-diffeomorphic structural manifolds, then it's going to be a whole bunch. It's a very short 6.5 pages, but yeah, it's one of the landmark papers. So this is one use of that. Okay, so these are some 7 manifolds, each homeomorphic. So there you use Morse theorem, Reed's theorem. And when I say diffeomorphic cluster, I mean the standard unit sphere in R, the usual that is, they are all topological 7 spheres, but somehow you cannot have a smooth map from this manifold to this manifold which has a smooth. Okay. Yeah. So anyway, this is, treat this as a black box. I'm just saying that you can use this, but of course you have to know how to construct a Morse function with the right number of people. So for that you have to know how this n is constructed. You cannot arbitrarily construct a Morse function with the appropriate trivial point or an arbitrary. Okay. Yes. Yes. Oh, yeah. So the point is, okay, so the idea is, the initial idea is pretty simple. If you look at the standard Sn, right? The standard Sn lives in Rn plus 1. It's the boundary of the unit form, which is the smooth n plus 1 number. Then you want to show that these L7s are not boundaries of smooth H-band. Forget ball, not boundaries of smooth H-band of any kind of H-band. So for that you have to invoke quantizing classes and invariants to such things. And that's the initial thing. That if it was diffeomorphic, then this would have been the boundary of an 8 ball. In particular, it would be the boundary of some smooth 8. But this is an 8 manifold with boundary. You have some quantizing class with unique force. So you can pair certain things and pick up some invariants and then get a contradiction from it. So there, I mean, he introduces an invariant called the lambda invariant, which requires the first quantizing class of the H-band code and some other things. But this has no internal homology. This is topologically S7. This only has H0 and H7. There is no internal. But the 8 manifold that you have, you cannot be a ball of dimension. Some 8 manifold might have some intermediate homology. Since it has boundary, he uses the quantizing classes to construct an invariant lambda and then uses that to and uses other results about quantizing classes. Yes, any other? Okay, so I wanted to okay, let me introduce yeah, so here in this example, remember I'm not going to say anything more about this, but I'm going to extract from this what I said. I said these M7s were not arbitrary 7 manifolds, they are constructed as S3 bundles over S4. Okay? And let me repeat. If you are seeing such a notation for the first time. I mean, this is, I guess, sometimes people might write it in one for a horizontal line just as an efficient use of spaces. I would rather if there's space, write it this way. So usually this stands for typically the notation for a fiber bundle, which means this is the total space. This is mapping to this is the base space. And this is the hook arrow, this is prototypical fiber. So this is the fiber bundle.